All right, in this video, we're going to talk about damping, and we're going to talk about resonance and this idea of natural frequency, probably not in that order. We're actually going to start with resonance. So what is resonance? So first of all, we need to just kind of have a discussion about what resonance actually means and effectively come to some sort of understanding about some examples. And really the most common example is a swing. Okay, so when someone is on a swing, so here is my awful drawing of a swing. And here is a person on that swing. The aim of a swing is to go higher and higher, isn't it? And this is effectively just a big pendulum. And what you'll find is, what do you do when you are on a swing? Well, what you're doing is you're moving your legs to effectively cause the swing to resonate. So the movement of your legs backwards and forwards cause resonance. So resonance is this feature of a pendulum where the amplitude continually increases and increases over time because you are adding in a oscillation which in this case matches the natural frequency. Now, depending on the length of the pendulum, depends on how quickly, effectively, you move your legs. Now, if you move your legs at a slower or faster speed, you won't actually complete the resonance correctly. You won't be adding the energy in the right place to cause an increasing amplitude, which effectively leads to you having fun or a child having fun. So let's look at this idea of natural frequency now. So natural frequency is just the frequency that any pendulum has as a result of what it is. And you'll remember that from the equation T is equal to 2 pi L over G, which may not be part of your specification, but it is the equation or formula for a pendulum. Now, hopefully you're remembering that 1 over T is equal to the frequency. And in this case, we can rearrange this equation to show what the natural frequency is of this pendulum, because it's the frequency that any pendulum of this length will have. Because think about what's the only variable in this? Well, the only variable is L, unless you go ahead and take this pendulum up to a different planet. You're going to have a different value of G, so or higher in the atmosphere, for example. But assuming that most of your pendulums are going to be used on Earth, you can achieve G stays the same at 9.81, but the only factor that is changing is L. So basically, any pendulum that is this length will have the same natural frequency because it will have the same time period. So the natural frequency is worked out as frequency would be 1 over this whole equation here, 2 pi root L over G, or you could rewrite this quite nicely as, and I'm going to jump a little bit of algebra here, root G over 2 pi root L. So that's just a nice equation for the natural frequency of a pendulum. And that is the frequency that if your legs on this swing are moving at that frequency as well, so your legs are moving backwards and forwards at that frequency, then you are going to create resonance. The amplitude will increase and increase and increase continually until either you break the swing or you reach a maximum height that you can do force with your legs. So the natural frequency here is what you have to match in order to get resonance. So we call this forced forced oscillations. So we're forcing this to oscillate, and we're forcing to oscillate more and more and more. So it's the idea of forced oscillations. So forced oscillations are caused in a situation where the natural frequency of an object matches the driving frequency. So let's write that down. So resonance occurs when the driving frequency matches the natural frequency. Now, there are all kinds of interesting examples that you can look up online of where resonance is potentially a good thing or even a bad thing. Very specifically bad things, because actually resonance can cause some pretty awful catastrophes, specifically relating to bridges and swing bridges and whatnot. So feel free to Google or YouTube that for a good watch, because there are some very fascinating videos about how resonance has caused destruction. But this is a nice friendly example how resonance allows us to enjoy being at a playground. So this is one side of resonance, but the other side is what happens when we try to reduce the energy. So effectively here we are increasing the energy in a pendulum because we're increasing the amplitude, as you saw from the energy or as you will have seen from the energy video for simple harmonic motion, that the amplitude effectively defines how much potential energy and retrospectively how much kinetic energy it would have at the equilibrium. So it's all about increasing the amounts of energy. So there is an increasing total energy because you're increasing the potential, hence you'll increase the kinetics, so the overall is increasing as a result of resonance. Right, so let's take a break, and in the next video we'll look at damping.